Now as important functions are ready, it is important to go for the Simulink block diagram so that we can access or interact all these functions all together and get a value information or value we have required. That is all the state variables, how they are behaving over the time. So let us go to develop the Simulink block diagrams. To do that, first we need to type Simulink over here and it will initialize the Simulink. We will directly go for the blank environment, and this is the complete blank environment. From the blank environment we are creating the loop inside it, and we are going to get all the results or dynamic response of the system from our equation of motions and forces. So first what we need to have, we need to save this file first. So let us save as airship nonlinear dynamics, airship nonlinear dynamics Simulink. Okay, and let's give the year date 2024. So this is what it is. Now we have the year date as well in the file. So file is created and it is blank file. So I need to work on this blank file to create something valuable. Now what we need actually, we need to access these functions in the environment, and we need to convert these dots, basically integrate these dots to estimate the state variables. Alright, and we have the dot over here as well, output. So all these three functions is having the dot as an output, not the required state variables. So we need to integrate them. Simulink is going to be very helpful for that. We don't need to write anything about it. We just need to use a simple block, which is integrator block, which will be helpful to integrate everything. So let us go. The important thing is we need to access these functions. So we need to have this name of these functions. So we'll copying first and then going to the block diagram. So let us open this block here. So first we'll access this function. How to do that? We can go to this user defined function section, and here we can use this interpreted Matlab function. Because we have already interpreted the function or developed the function, we will use this block simply here. So this will be the first block, and this block will be for our nonlinear dynamic equation of motion. Then we also need to estimate the Euler angle, second function, and then we also need to estimate the position, third function. What you need to do, you need to double click on this, and here at the Matlab function we need to change the name of this. So our Matlab function is airship nonlinear dynamics, which will give v dot as an output. So apply and hit OK. Now we have another, this function will be estimating the Euler's angle. So let us go to the Euler's angles and copy this function name, and then go back to this. Here we need to change this. Now this will estimate the Euler's angles. Now one more function is there. This is position with respect to earth. That function we need to again define over here. So we will define it like this. Very simple. And in the simple way we have estimated the Euler's angles. So we now name it as Euler angle rate, because it is giving the rate, not directly the angle. And this is position rate with respect to earth. So this is what we are getting from these two functions. Dynamic equation of motion. Okay, equations of motion. So all forces and moments are solved in this function, and we have output as v dot. Here we'll write u dot, v dot, w dot, and w dot, p dot, q dot, and r dot. These are the variables we are going to use or we are going to get from this function, and we need to integrate them. Then only we will be able to get u, v, w, p, q, r, which will be helpful to estimate Euler angle rate and position rate. So to integrate that, we need to go here, and here you need to type integrator. So integrator, the second option is here. 1 by s, you can use this one. What this integrator do, this will use Runge-Kutta fourth order method to solve this nonlinear equations of motion and provide you the solution of the equation of motion. So basically we have nonlinear equation of motion which is going to be integrate using the Runge-Kutta fourth order method, and we will get the output as UVW PQR. So here we will get UVW PQR. Alright, now Euler's angles. What are the requirements for the Euler's angles? So let us go to the function. So requirements are PQR and phi theta psi. Okay, now PQR we can get from here, but phi theta psi we don't have. So from where we'll get the phi theta psi? This function itself integrate and give us the phi theta psi. So we can, the output of this function will be Euler angle, rate of change of Euler angle. So integrate this and we will get what? Integrate this, we will get our Euler's angles, phi theta psi, right? So we'll integrate this and we'll get phi theta psi. So here phi theta psi, this is what they will get. So phi theta psi we are getting from here, and this phi theta psi and this PQR from here we can use to estimate the Euler's angle itself. Now how to combine these two things and add into this wire? To do that we need to use mux command. So mux we will use. Here we have mux and we have two variables. One wire variable is from here and another wire variable is from here. So basically we are joining them, and this is going to be connection. So one connection is done. Now what are the order? Order is like top is first and next is, it's go like first, second, third and fourth. So in the first we have 1 2 3 4 5 6 already, and then we have the second 7 8 9 10, 7 8 9, basically 9 up to 9. So 1 2 3 4 5 6 7 8 9. So order over here is, order here will be equal to U V W P Q R phi theta and psi, right? So this will be the order. So let us check in the function is whether it is following the same order or not. So over here we have 1 2 3 as a phi theta psi, which is not so correct. So what we will do, we will reverse this and add this over here. So now we have order phi theta psi first, phi, which is required, right? So we have order phi theta psi. Now first three order are there. Now after that we have the connection of UVW and PQR. So PQR will be 7 8 and 9. So here the PQR are 4 5 and 6. We need to change to 7 8 and 9. Rest of them are fine. 1 2 3 7 8 and 9. We are not accessing this velocity component, we don't need it. So right now this Euler's angle function is ready, which we can use or we can print as well. Okay, so this is what is the Euler angles. Now what are the requirement for the position with respect to Earth? Let us go to the function. So the requirements are UVW. So UVW we can get directly from here. Again we need to use mux because we need to connect other variables. So we can use UVW from here. Order is first, second and third, and let's see here what is the order. First, second, third. So we don't need to change anything, directly it's getting the results. Next input will be in this phi theta psi. From where we are getting phi theta psi? From here we can get. So let us connect this from this. Alright, so this one is giving you phi theta psi. this one is giving you UVW. Now all the requirements are complete in an order. UVW phi theta psi, right? UVW phi theta psi in an order, no problem. And we have the estimation of x dot, y dot, w dot. So now we need to integrate this as well. So let us integrate this with respect to initial position. So after the integration we will get x, y and z. So this is what we are getting here. So this is where we are getting x, y, z. The requirement of dynamic equation of motion is basically UVW, PQR, phi theta psi and x, y, z. UVW, PQR we can directly get from here, phi theta psi we can get from here, and xyz we can get from here. So we need at least 3 mux input. So we'll copy this, paste it over here and double click on it and use 3. Double click, after double click you can change number of input want. So 3 we have required 3, so we use 3, elongate it and then radius. So now first we'll have input as UVW PQR. Second we have input as phi theta and psi, and third we will have input as x, y and z. Ready? So now it is complete, I think. Now we need to check the order. Order is UVW 1 2 3, PQR 4 5 6, phi theta psi 7 8 9, and then 10 9 10 11 11 12 are the order. So UV 1 2 3 4 5 6 7 8 9, yes. So x E will be equal to airship, basically airship 10, and then YE will be equal to airship 11. That is it. So YE we can change, YE will be equal to, but one more important variable we are going to use, which is over here, airship 12, which is the z value. Now we are ready with this diagram here. So here we need to define the initial conditions. So UVW and PQR initial conditions are defined. Now next is integration of this one. It has phi theta and psi integration. So we will give the initial condition as S phi naught, S theta naught and S psi naught. These are the important things: phi naught, theta naught and psi naught. Phi naught, theta naught and psi naught. So these are integrated. Now here also we need to define. So here it is taking positions. So S x E naught, S x y E naught and S z E naught. These are the variables or initial conditions. So we have defined. Now clearly every integration is defined and all is fine. So in this case we are ready to have our first look of the results.